All right, folks, we're getting ready to start section 3.4, and this is kind of a midway point in the chapter. I've told you that chapter 3's title is Applications of Derivatives, but I think a better title would be Function Analysis. We've already talked about finding absolute extrema on a closed interval in 3.1. In section 3.2, we talked about the mean value theorem. In 3.3, we talked about how to test if a function is increasing or decreasing on an interval, as well as the first derivative test to find local extrema on an interval. So now we're going to move into section 3.4, and these problems I'm going to give you here today I like to call 1-pepper calculus and 4-pepper algebra, because the calculus that we're going to do, not too tricky, but the algebra required to do what we're asked is going to be really hard. And this is just a preview. The things we're doing here, notice I've asked you to take to do a sign chart of the first and the second derivative of each of the functions. These are things we've done before, but in this section we're going to go a little deeper and find out what they actually mean. Okay, so let's go ahead and get started. You'll notice to start here I got a rational function, 2x squared divided by the quantity x squared minus 4. I'm going to quickly just jot down the domain of this bad boy. I know the domain x cannot equal plus or minus 2, because that'll give me a 0 in my denominator. So now I'm going to just go ahead and rip through the first derivative. I've got a quotient, so I'm going to use the quotient rule. Low d high minus high d low divided by low squared. So that's my unsimplified first derivative with the quotient rule. Really not very helpful in this form, because the only thing I can do if I wanted to construct a sign chart for this is, I can see what happens in the denominator, because that's pretty compact, but I'm going to need to expand and simplify the numerator to really analyze this derivative in more detail. All right, folks, there's my first derivative, and that's as simplified as it's going to get. So now we can go ahead and make a sign chart for that. I know that f prime of x will equal 0 when the numerator equals 0. That occurs at x equals 0. The denominator will equal 0 at plus or minus 2, and those values aren't even in the domain of the function. So I'm going to include them on my sign chart, but I'm going to mark them as not in the domain. So I'm going to start with the number line. I'm going to put f prime of x on the top, x on the bottom. I have a couple numbers I'm going to mark. Definitely going to put 0, because that's when f prime equals 0. I'm going to put positive and negative 2 as restricted values. And then I'm going to go ahead and look at, pick test points on each of these intervals to figure out what the sign of the first derivative is. The first thing I notice is that my denominator, x squared minus 4, that quantity gets squared, so for all real numbers, that will be a positive value. That means the numerator determines the sign of my derivative. If I pick a test point out here to the right of x equals 2, I'm going to have a positive number times negative 16. That's going to give me a negative value in that interval. If I pick a number between 0 and 2, same thing. So if I pick positive 1 for x, I'm going to have negative 16 times positive 1. That's still a negative value. Once I cross over x equals 0, though, to the left, then I'm going to have a negative input, and I'm going to have two negative numbers multiplied together in my numerator. That'll result in a positive. Same thing when I go to the left of negative 2. So there's the completed sign chart for the first derivative. Let's go ahead and do the second now. When I do the second derivative, again, I need the quotient rule, because my first derivative is a quotient, and I'm going to do low d high minus high d low divided by low squared. Okay, folks, I hope you noticed that I had to use a chain rule there because my denominator is a composite function, so the chain rule piece came into play right here. So I took the derivative of the outside function, which is a function squared, and then I multiplied by the derivative of the inside, which is that x squared minus 4 piece. Okay, so I'm ready to simplify this now, but I want to encourage you to use caution. Anytime you're taking any rational type function and finding its second derivative, before you expand and simplify the numerator, I want you to look very carefully for any common factors that you might be able to cancel out. If you look very carefully, you'll see that there's a factor of x squared minus 4 all over this thing. I'm going to go ahead and factor that out of the numerator before I try to simplify. So I went ahead and factored out an x squared minus 4 for my numerator. I hope you noticed here that I did take the liberty of switching those to positive numbers because I had the opposite of negative 16x. I went ahead and switched that to a positive just to make things a little bit easier down the road here. But I factored out an x squared minus 4 from my numerator. There it is. And I hope you notice that we have that same term as a factor in the denominator. So I can cancel one each from the numerator and the denominator. So this one will disappear, and this one will turn into a cube. So let's go ahead and now I'm going to try and simplify what's left up here, and we'll see what we have. Okay, folks, so there's my simplified second derivative. And I think from this point we can make a sign chart from this bad boy. I notice that I have a value of plus or minus 2 in my denominator. That will make that 0, but we already know that that's not in the domain of the function. We'll include it on the sign chart as a restricted value. My numerator, take a close look at that bad boy. I have 48x squared plus 64. That's always positive, okay? Because I have 48 times a square number. For all real numbers, that's positive, and then I add a positive to it. So I'm just going to make a note here that this is always positive. So the sign chart of the second derivative will be 100% determined by what the sign of the denominator is. So let's go ahead and take a look at that. So we got f double prime of x here, x here. We've got negative 2, and that is a terrible number 2. Negative 2, which is a restricted value. Positive 2, which is a restricted value. And we have no zeros for f double prime, no zeros whatsoever. Let's go ahead and pick a test point like, oh, I don't know, positive 3 seems like a nice number. If I plug positive 3 in for my denominator, I get 3 squared, which is 9. 9 minus 4, which is positive, and I cube it, it remains positive. Let's jump across x equals 2 and go pick a test point like x equals 0. 0 squared minus 4 is negative 4, and then when I cube negative 4, it is a negative value. So I have negative values on that interval for the second derivative. Then jumping across x equals negative 2, we'll pick a test point out here like negative 3. When I square that, it will become positive 9, subtract 4, gives me a positive number. I cube it, it stays positive. So there, folks, is the sign chart for the second derivative. Let's go ahead and shut this video down, and then we'll take a look at the 4-pepper algebra problem on the back side.